Alright, continuing with this video series, or in the series. This is an exam video, so it's sort of a review of some of the other stuff, and I think we're going to do resonance now, I think. Maybe. Perhaps. I think.
Okay, let's now talk about standing waves. Let's start with strings again. This is a string, length L, and I generate in this string a standing wave.
Sort of the partially sort of annoying is that they don't really get to the mechanics, the actual physical properties that the string or the material has to have, like the surface of water and different things, and talking about the fact that, what this is about is the fact that elements that are moving are adheres to other elements that are moving, and that this is a lot about the fact that these things are connected to each other and have to drag each other along to go where they want to go, sort of. Sort of.
Standing waves can only be generated at very discrete frequencies for very special wavelengths. It's a resonance phenomenon. And the lowest frequency for which this occurs will make the string oscillate in this fashion.
Up and down. So the reflection and the two complementary waves.
The string will do this.
Yes.
This is called the fundamental, also the first harmonic.
So the first wave goes, and then it comes back this way, and so there's no chance of interfering with each other. Well, there's no chance because of the fact that they're in a different period of time. So that's one reason. But they won't have two pieces of energy going through the rope at the same time, so that's the catch. So the real catch of the destructive interference happens when you start moving two pieces in conflicting directions. So this wave's going down, this wave's going up. Obviously this matter can't do that, and it basically cancels out. So it actually kills the force. So the only resonance means what gets kept. So that's all it means, is the energy is kept. It doesn't get destroyed. So things that are obeying the resonant frequencies, the harmonics, the non-conflicting waves, that is, waves moving this way aren't in conflict with waves moving that way. They're both going up at the same time. They're both going down at the same time. Those waves stay. That energy is preserved. The energy that's in conflict is destroyed and canceled. And destroyed is not the right word. And so it has every appearance of saying this is what I like, but the like is just this is what I don't like is really the issue. It's the waves killing each other that makes this appear as the reality.
Then there is a second harmonic, which is the next frequency up for which it will resonate, which adds an extra note. There's already a note here and a note there, and the system will then oscillate like so. And then, so this is the second harmonic. And then I can go to the third harmonic, and I can continue forever, not quite, but I can continue quite a bit. And this now would be the third harmonic. And the frequencies that are the resonant frequencies are given by f of n, n being Nancy, that means either 1 or 2 or 3 or 4, 1 being the fundamental, 2 being the second harmonic. This frequency is given n times v divided by 2L, whereby v is the speed of propagation of a disturbance along the direction of the string. And L, in this case, is the length. And the associated wavelengths, lambda, for that particular harmonic is 2L divided by n. If you put in any...
So, just as a general commentary, see, all this is really nice when they're just doing this with mechanical waves, but then they try to apply these same formulas to what light is doing. While it has some things in similar, in its force, its energy, it's made of the same thing in the sense that the stuff that's making the rope move is energy, is force, is little bits of stuff, electricity and stuff like that, moving electrons and moving atoms. And so it's made of the same thing, but it's such a distant version of it in the sense that you do have this adhesion between the atoms, and you have all this stuff going on inside the atoms, and it's a much more complex system. And they end up applying it as if it can be applied to the elemental thing that's causing the effect. And I think it's a huge mistake there.
Equals 1, you see that the wavelength is indeed twice the length. And if you put in n equals 2, you see that the wavelength is exactly L. So let us write down, for the fundamental,
so if you were talking about sound, for example, you would know that it's not a rope. But you would know that it is little bits that are pushing into each other and creating, you have them separated at a distance, then they're close to each other, so you end up having more mass of something in an area. And it's more mass, so you're increasing the density, and the density is moving as a wave. But it's really wrong to compare what's happening inside a rope to what's happening as a compression wave.
Equation for a standing wave. Y1. 1 refers to the fundamental. Would be Y01 times the cosine of omega 1t times the sine of k1x. This is very different from a traveling wave. All the time information now here is decoupled from the spatial information. K1 is again, as before, you write down a nicer K1, 2 pi divided by lambda. And omega 1 is 2 pi times F1. What is so special here is that there are points here, values for x, for which the sign becomes 0. In the case of the fundamental, put in x equals 0, and you find that that sign is always 0. But if you put in x equals L, you can check that, it's also 0. And if you go to the second harmonic, you will find that the sign is 0 there as well. And so there are points now which never move. We call those nodes. That's very characteristic for a standing wave. I could go to the second harmonic, and all I would have to do is put here a 2, and here a 2, and here a 2, and here a 2. It would have its own little amplitude, which would be this. It would have its own frequency, but that frequency, omega 2, is non-negotiable. That must be 2 omega 1. And if I go to the third harmonic, then omega 3 is going to be 3 omega 1. But it has its own wavelength. You get k of 2 would be 2 pi divided by lambda 2. And the lambda.
But its wavelength is clearly going to be a 1/3 derivative of the original wavelength. There's no surprise there. I mean, well, whatever.
The lambdas are given by this relationship. I want you to get a few minutes rest now, so that you can digest this, and then we'll go to electromagnetic standing waves. And I want you to see this again.
So again, you'll go to electromagnetic standing waves, and it's, like I said, I think there's just a big mistake in comparing a complex system to the real elemental system. So when you're getting to electromagnetic, you're getting to what's really happening inside the rope. Inside the rope, not as a byproduct of the, like I said, what the rope does, what we see, is a consequence of the elemental function.
You've seen that before, but I want you to see it in a way that you have not seen it yet. We have here a rubber hose, which we can oscillate, and we're going to oscillate it in such a way, at least that's our goal, to get the third harmonic. It's not so easy to get exactly on resonance, but we will try that. And Marcos decided to make it very beautiful for you, so he's going to put up a black screen there, because once we are at resonance, we're going to strobe the string, so that you will in fact be able to follow the motion. Your eyes can't see what's going up and what's going down, it goes too fast. But when we strobe it, we can slow that down, make the thing actually stand still.
Yeah, well, we can do that with on a computer. So, yes, I can see what's going up and what's going down, and so, yeah, nice, but
Still. And that's our objective.
You already drew it, so we already get it.
So you'll be able to see that. And so let me turn on the strobe.
So obviously, at any one point, the rope can't be conflicted. It has to be in one place. It can't be in two places. So if any energy was in the rope that was going the wrong way, that energy would have to be annihilated. And so the only energy that is preserved is all the movement that are not doing two different things at the same time. I mean, going in two directions.
And this black background will help. The strobe frequency is not exactly the same as the frequency of the oscillating string, so that allows you to actually see the slow motion. And no one is arguing with me, right? When the center portion is down, the left and the right portion are up, and vice versa. So you can really see now the characteristics of this standing wave. Notice you see in this case 4 nodes. One at each
Could see it better without the augmentation, ironically.
either end, and you see 2 nodes in the middle. That is where this sine of that curve is always 0. I can add another strobe light at a slightly different frequency. I collaborated for a few years with an artist. His name was Tsai. He worked at the Center for Advanced Visual Studies here at MIT, and he actually made art by oscillating objects at resonance frequency, rods and strings, and he strobed them in a way that I'm doing. So I actually learned this from him. Quite pretty, but also very instructive. You can really see what's going on. In green, you see this string at a different moment in time than you see it in red. And as I said, I purposely made the frequencies of the strobe a little different.
Yes, like I say, just freeze frame works just as good, or better. However you look at it. Nothing needs to be said. I just think that, like I said, this whole resonance thing is really important in the sense of understanding that it really has to do with preserving energy. And so it's another way of storing energy is resonance. It's another method, another mechanism where the energy stays in the system as long as it's harmonic, and as long as it's compatible, as long as it's constructive, as long as it's interacting passively with the energy that already exists in the system. So if it's passive to the energy that exists in the system, it's retained and keeps reflecting. And so there, in a way, it's a kind of capacitor. It's a kind of battery. I think that's something I didn't understand until recently, and it makes resonance makes much more sense now. Just understanding what's really happening is you're just storing a certain frequency. So a certain frequency is stored in the system, and it's a closed system. When it doesn't have open ends at both ends, that's reflecting. That's going to store energy.
Thanks, Marcos. As you perhaps remember, you can also generate a standing wave in air itself. Wind instruments are nothing but air columns which go into resonance. If I have here a wind instrument which is open and open on both sides, but this is the length of that instrument, then the frequencies that I can generate are given by this equation. The only fundamental difference.
So the only thing lacking in these explanations is where the frequencies are, and they have to be in the material of the thing itself. They're being stored in whatever the tube is made out of.
Between the strings and the wind instruments is that with strings you can change V at will, more or less. You can choose different materials through which the speed of propagation is different, and you can also change the tension. If you increase the tension, this V goes up. So you can give a violin 4 different strings that give you 4 different fundamentals. With a wind instrument, you cannot manipulate V, because V is the speed of sound. And so that V of air at room temperature is 340 meters per second. That's not.
So I don't think that's the only V in the equation, though. I think the V of the vibrations in the tube are also playing a part in this. So I think it's an oversimplification. That's what I think.
Non-negotiable. And so you can, with wind instruments, you can very easily predict the frequencies that you're going to hear. I have here a pipe which is open and open on both sides, 1.5 meters long, and if I apply that equation, I will find that the fundamental would be at 113 hertz. Perhaps you remember that I told you that resonances can occur when you sometimes least expect them. Just by blowing air, you can get resonances. If you take a wind instrument and you start to blow air, it excites resonances. Remember that the Tacoma Bridge, there was wind, and it went into resonance. It was very destructive. Well, here we have a system that we can also make go into resonance when you least expect it. We have a copper grid here, and I'm going to heat that grid. And when I heat the grid, you get an airflow going through it.
So, but the key is that yes, it's a grating. Really, you can use different materials to create a bunch of little holes that the air has to go through. So that's what it's really doing. It's creating a whole bunch of different surfaces that the air has to travel through, and so surfaces will end up vibrating, I would suspect.
There. That all by itself will not make it go into resonance. But when I take my heat source away and that grid starts to cool, it goes into resonance.
No explanation for why the difference. So it must really have to do with the pressure of the heating is less than the pressure of the cooling. So the air, the hot air, when the grating starts to cool, the cooling air goes through with more pressure, more velocity than the hot air did. It's the only way I could make any sense out of it.
So I'm going to heat it now. Will take a while. If I heat it too long, the copper grid will melt. Many years ago, when I was doing this with a very short burner, the molten copper came down on my hands, which was not funny, believe me. If I don't do it long enough, it won't go into resonance.
You could just use like stainless steel, wires or something. Just a ball of wire. Stick that up in there. And it would work also.
So I'm sort of guessing this a little. On the 13 hertz.
So I think my previous explanation was wrong in the sense that what's really happening is when he's heating it, the air is below the grating is being compressed, and so it's getting very hot. And so there's not a big difference between the air above and the air below. So there's not much convection. He's just heating the metal. But once he takes away the burner, then the cold air goes in, and the cold air gets a lot of convection, and so that shoots up very fast. So he's changed the velocity of the air, which is sort of, as it says, you can't change the velocity, but in a way you can, because you're creating the velocity that creates the sound is different than the speed of the sound through the system. So the slowness of the sound vibrations is connected, but it's different than the speed of the air that causes the vibration.
All right.
So there, I figured that out. That's how it works. Okay, so it's just about the temperature differences. So once he takes the burner away, there's a huge temperature difference. Now the cold air is getting in. Cold air rushes through the screen and vibrates the hell out of everything, and that's the sound that's banging its way through the pipe.
Right, standing electromagnetic waves. When we go to standing electromagnetic waves, let me stay on the center board here. The situation almost identical to standing waves on a string. Again, we have nodes. We have locations where the electric field is always zero.
So again, a node doesn't really mean anything. In electricity, it's so much different than the fact that the nodes in the harmonics, the nodes are just the places where something out of the reflexor goes through. So the nodes are just going from I have a downward direction to I have an upward direction. So the nodes are just the points where you're changing direction, where you're in the where every direction change, there'll be one node, right? Yeah, every direction change, there'll be a node. So halfway through that direction change. So that's very different, passing through a midpoint of a plus and a minus, so to speak. It's very different than, an oscillation that is Obviously, the rope is moving up and down is what the rope is doing, and there is a midpoint, and the nodes are on that midpoint. That's not surprising. But electromagnetic waves, as they're calling them, they're not nodes. They're just, there is compression, there's no compression. There's corpuscle, there's no corpuscle. There's photon, there's no photon. Very different. I would argue that this is where they're mating the wrong animals, and they're going to end up with something not right.
Very, very different from a traveling wave. I refer you to problem 9.4, where you will see a standing electromagnetic wave, which, just like we had with the string, it has exactly this form. The time domain is decoupled from the spatial domain. The only complication that you have with a standing wave electromagnetic is that it is not so easy to find the associated magnetic field. And therefore, I refer you to that problem 9.4 if you want to revisit that.
Yes, well, you're not going to find either field as described as electric or magnetic, because the thing itself is force. It's a something, it's a stuff that moves the speed of light, and all you're doing is saying how much of that stuff at a certain color, electron important or proton important, what mixture of it you're sending. So there's just an amount and a mixture, and that's it. There's an amount and a color.
Polarization. Oh, we want to see the subjects again, see where we are on the list.
You moved right past the electromagnetic wave to polarization, so we didn't get any photons in here.
But I think the time has come to talk a little bit about polarization. That's right. Polarization. Let's take electromagnetic waves.
So they really don't know what polarization is. Clearly the rope has an obvious polarization, so that gives it, that makes things simple. But that's because they're turning everything into a sine wave. So they're taking a rope, a simple example of the force moving through a stiff object, and they've decided that the things that aren't in stiff objects are doing the same ropey stuff, and they're not moving like a rope. The force isn't manifested as a rope. A wire holding electricity doesn't move like a rope. And there's a reason it doesn't do that, is because that way of visualizing it is just wrong.
Comes straight out of the blackboard to you. And I call this the y direction, and I call this the z direction, the x direction, and z is to you. Notice x cross y is z, always in my case, right-handed coordinate system. And so the electric field vector of the plane wave that is coming out of the blackboard, let us assume that the electric vector is oscillating like so, with angular frequency omega. If this is a straight line, we call that linearly polarized radiation. Could be.
So again, he's choosing the electric, but you could choose the magnetic. It doesn't really matter that they're saying it's polarized in a direction, because they're saying there's some sort of this going on as something's moving, and there's none of that going on. They've never attempted, well, I don't know if they've never attempted, but they they clearly imply as if they have some sort of hard evidence that there's some sort of this going on, when they don't have any hard evidence for anything like that. And there are other ways of describing what polarization is. I'll go back to my description. Maybe there's not a ton of them. I had to think about it for quite a while before I fell upon the idea that photons, when they're emitted, are not in perfect alignment. And that explains the polarization. If you want to use your snaky thing, it means the snake is a little higher over here than he is. He has a low belly, and then he goes back to here, maybe he goes up to here, so he has a lack of perfect alignment. And that would have to do with the atom itself having a consistent jitter, so it's moving in one vector. Its momentum of every atom is always in one direction for brief periods of time. And so it's just being emitted at different locations, but they're all parallel, so they don't diverge. So the polarization stays consistent because the individual photons aren't flying perfectly behind each other. Just as you couldn't shoot bullets right behind each other as a practical matter. Your hand will move a little bit.
radio emission, as we did with the 75 megahertz transmitter. It can also be visible light. As long as the E vector stays along a straight line, we call it linearly polarized electromagnetic radiation. Electromagnetic radiation, including radio waves, including visible light, can be circularly polarized, in which case the electric vector doesn't oscillate like you see here, but always has the same strength and is rotating around in a circle, either in this direction or in this direction. And it's very easy to make, actually. I could have done that.
So that somehow they think it can corkscrew its way through the filter that way. And they think that when they always draw it as circular polarized, usually because it's the magnetic and electric fields are turning as they're going forward. So they, give it a double helix kind of look.
Here in lectures, but I never did. Suppose we have an antenna in the y direction, and we have another one in the x direction, like our 75 megahertz transmitter was this copper bar in this direction. And suppose each one radiates with exactly the same value for E0, with exactly the same frequency, but they're 90 degrees out of phase. That's not so difficult to arrange.
Yeah, you just pump the same frequency into two different antennas in two different orientations, but the individual photons are not going to be circularly polarized. It's not going to happen.
I would get an EX, which would be E0, and if I pick my value for Z, let's take Z equals 0. Who cares where you are in this line? So there is no KZ term, so we simply have a cosine omega t here. So this is the component of the electric vector in the direction of x. And let the one in the y direction be 90 degrees out of phase, but must have exactly the same amplitude. So 90 degrees out of phase would, for instance, be sine omega t.
All right, but 90 degrees out of phase, he's talking about the phase of its polarization. It's not going to be the phase of the photons. So that's just a deception, in my opinion. I don't think so.
Omegas must be the same. You get circularly polarized radiation. And so the net electric field vector, the one that you will experience sitting here on the z-axis, will be Ex in the x direction plus Ey in the y direction.
So this is very sloppy in terms, in my opinion, of diagramming that somehow you've created circular polarized light by having two antennas that are sending out the same signal, and then claiming that somehow they're out of sync out of phase with each other when they're not.
And so the magnitude of this vector will be the square root of Ex squared plus Ey squared, and that is E0. Because sine squared omega t plus cosine squared omega t is 1. And so you get under the square root E0 squared.
I don't know. He's almost saying that, oh, you have two antennas, and now you put a polarizing filter in front of it, and you'll get half the light. Yeah, sure you will. You'll get half the amount that both antennas are producing. One antenna you get all of it, and the other antenna you get none of it. Big surprise? No.
Times 1, and so that's E0. And so you see that the amplitude is always E0. You see that here in front of you. And so it's going to rotate around. When it's maximum in Y, then it is 0 in X. And when it is maximum in X, it is 0 in Y. And so therefore you get this rotation.
So just nonsense. This was just nonsense. Sorry, this is just nonsense, right? I mean, clearly you're producing the radiation, okay, coming off the antenna is coming off in these planes anyway. So let's understand it's coming out this way, in rays. Going up, flat little planes of radiation going in all directions. It's like layers of a pie. This is the surface, the round surface is where the radiation is coming out of. And so one antenna, the round surface is this way, the other antenna, the round surface is this way. So obviously you can just see orientation-wise they're just opposite. Okay, they're like the frisbee. You got frisbees going this way and you got frisbees going this way. That means obviously when you put both antennas and then you filter it, the filter, depending on which filter it is only going to get only half the frisbees are going to get through. I mean, there's nothing circular here. So this is just rubbish.
either this way or that way, depending upon how the phase delay is arranged. And you can turn this into elliptical polarized radiation by simply, for instance, putting a 2 here. If you put a 2 there, or let me put a 2 in the x direction, because I have more room in the x direction on the backboard. So if I put a 2 here, that means that in the x direction, I can go twice as far as I can go in the y direction. And so now the E vector...
Yeah, so now, quite obviously, again, I have twice as much stuff coming out of this one as I have out of this one. You know, yes, I'll get twice as much from this one as that one. You haven't created anything elliptical. There's no elliptical photon. There's no circular photon, except circular, in my opinion, would be light that doesn't have a polarization because they are lined up.
Will go like this. You see, this now is twice as much as this, and so now I have elliptically polarized radiation. Okay, so far as for the...
Yeah, so far that was just rubbish. I mean, there's no evidence of this. It doesn't used in the real world anywhere. Nobody uses elliptically polarized light to do anything. It has no value. It's meaningless, blah, blah, blah.
Polarization is concerned. Let's talk about Snell's law.
So let's understand. He does make little speeches every now and then about understanding concepts. And there is no concepts here, right? There's just nothing as a concept. You're given nothing to grok as a mechanical function. Just math.
Snell's law was discovered 250 years before Maxwell. It's quite an amazing accomplishment. Even though you can derive it from Maxwell's equations, of course. But it was derived by this Dutchman 250 years earlier. And what the Snell's law tells us...
Well, I don't know if it was derived, so he uses a word like that, but I think what it was observed. It's a law that was observed.
Is that if we have light going from a medium 1 with index of refraction n1, going to medium 2 with index of refraction n2, this angle of incidence is theta 1. This is the normal to the surface. And we get some reflection. This angle is also theta 1.
So this reflection and refraction thing is interesting. I haven't been able to find a really good law to use to get the magnitudes of how much of the light goes through, because they always use a surface, and the catch is there's two surfaces to a piece of glass. And even if you were to use water as an example, there's going to end up being two surfaces, because if you just shoot it through the water, you'd have to have something catching it at the bottom. It's going to end up reflecting back. So there's more than one surface involved. They don't really talk about that, but this math applies to one surface. It doesn't apply to the second surface. So you have to do the math a second time for the second surface. I mean, to be doing it right. I mean, to be doing it as we commonly experience it. So I'm just saying that was sort of a mistake I was making. I was watching this stuff, and I'm thinking of that when he draws that line, he's drawing a piece of glass. And I'm thinking about this is the total effect off a piece of glass. It's not the total effect. It's off one surface. And there's a second surface, and that's where we see the consequences.
And then some of that light will enter into this medium, and this angle will then be theta 2. And Snell's law says that the sine of theta 1 divided by the sine of theta 2 is n1 divided by n2.
This sort of comes up with arguments about how much light goes through a piece of glass. So if I have a little piece of glass and I bend it at a 45-degree angle, what I observed on my porch was the amount of light reflecting seems to be equal to the amount of light going through. So the two beams seemed quite equal. And the math doesn't fit that if you're thinking about one surface. But if you think about the second surface being inside of glass and going from glass to air, the angles change. The angle for internal reflection goes way down to like 40 degrees. Lots of things change for that second beam of light, the one that goes through the first one, and then it has a different proportion numbers. between what will be internally reflected and what will be emitted. So, but yes, figuring out exactly what those totals are. Yeah, I just haven't seen. I mean, it should be on a chart somewhere. Piece of glass, this much light will reflect at this angle. 45-degree angle, a certain amount of photons will reflect, and a certain number will go through.
Always the medium where you're going is up. Medium where, it's the other way around. Good that I caught that. This is N2 divided by N1. So the medium that you're going is up, and the medium where you came from is down. And so it's immediately obvious that if N2 is larger than N1, that the angle of theta 2 is always smaller than theta 1. Let us assume now that you go from...
Right, and then you go from water to air. It's going to be exactly the opposite because the angle now goes towards the plane that you're reflecting off of. So when you're going to a lighter medium, it bends up, and when you're going to a heavier medium, it bends down. That's how I'd look at it. That's how I'd simplify it.
Air to glass, but that somehow you come out in the air again. So right here, this is your angle of incidence now. I call it I. It's clear that I is theta.
Well, this is good. At least now he's showing the entire, that there's two surfaces here.
That too. And here you're coming out of the medium in air again, and I call this angle R. And I'm going to ask you the question, what is that angle R? Some of you may have graded.
The angle is the same as the other angle because it comes out the same way, but he didn't draw it really quite right, but it's okay.
Insight, and immediately say, oh, well, it's obvious that it's going to be the same as theta 1. And that is indeed correct. You can easily see that because the sine of theta 1 divided by the sine of theta 2 at this transition at point A, so this is at point A, would be n of glass divided by n of air. And now we come here at this point B. So at point B, we get the sine of this angle of incidence I, which we know is theta 2, that's obvious, divided by the sine of R is now the one where we're going to, which is air, divided by the one where we were. So this is n air divided by n glass. And we already agreed that I is theta 2. And so when I multiply these two equations, on the right side I get exactly 1, independent of the color of the light. If blue light has a different index of refraction than red light, that doesn't matter because I have the same one here that I have there. And so you get exactly 1 on the right side, so you must get exactly 1 on the left side, and so the consequence is that theta 1 must be R. And so this angle here is the same as that angle, which is perhaps not so surprising, because these two planes are parallel to each other. If they were not parallel, as they were with one of your problems where we had a prism, then you would get a separation of the colors here, and then the red and the blue would come out in different directions. In this case, red and blue and green and yellow all come out in the same direction, and so you see white light when you look through plain parallel glass.
Just pointing out that if the angles are different, that means the distance will be different through the medium, and you'll hit it at a different angle. So each color will hit at a different angle.
For total reflection, I refer you to problem 9.8 if you can spare the time. You're going to have 5 problems. 2 of them have 1 question, 2 of them have 2 questions, and 1 has 4 true-false questions. For each correct answer, you get 4 points. For each wrong answer, I have to subtract 4 points. However, you don't have to answer. If you don't answer, you don't gain, you don't lose points. Now, before you hate me for subtracting 4 points, think about this for a minute. If you give true-false questions to a class of 5-year-olds, they will have half on average correct and half wrong. Yet, they deserve 0. So clearly, the only reasonable thing is that for a wrong answer, you must subtract points. But you don't have to answer. So if you...
Well, I know, but if you give them the option of not answering, then you're providing them the opportunity to cherry pick and pretend they knew it when they didn't know it. I mean, you're trying to test them to see if they know something. Well, if they don't know it, then they should get points off. They shouldn't be able to free ride. So that seems like a pointless.
You know the answer to 2 for sure out of 4, you could consider not to answer the other 2. That is your choice. I'll give you an example. The Benham top consists of several colors. When you rotate it fast, you see white light. That's wrong. That's false. Because the Benham top did not have several colors. And when we rotated it, We didn't see white lines. I'll give you another example. One of two tails of comets is due to radiation pressure, and the other is due to the solar wind. That's correct. We discussed that in lectures.
I'm sure the questions won't be that easy, but anyway, this kind of, seems they should be able to handle this.
Let me end with some fatherly advice. Read each problem at least twice, and do those problems first that you like the best, those that suit you the best. Never spend more than 10 minutes on one problem, then move to another. There is another review tomorrow evening for 3 hours by Ali Nayeri. You may want to attend that. And we also will provide you with tutoring this Sunday. Look at the web, because we will update it as the time comes. See you Monday. Have a good...
Blah, blah, blah. Okay. Well, might as well play till
weekend.
dark. Might as well get every bit of it. Alright. So, enough said. So an important feature that I think is missed in the conversations about resonance especially is the fact that it's another one of these things, like a capacitor and an inductor. They're all storage devices. Now, they don't store much, but they store energy. They collect it and preserve it. They reflect it eternally. And such.